So, we did some graphing by transformation. And on the previous page in the notes is just like a summary of what each of the different things in the formula right here do. This adds to that the order that you should resolve those things in. And we'll think about why in a little bit, but first let's just remember what each of those things do. So what happens to a function if you what happens to the graph of a function when you multiply that function by some number? Oh shoot, let's even just remind ourselves, right? There's nothing magic about these things. There's some function. Let's make it less even. So if there's a function f of x, let's set a constant 3. How does the purple graph compare with the red graph?
Vertical stretch of 3.
Yeah, vertical stretch. All the y values are multiplied by 3. And that 3 is, of course, because that constant is 3. So what will this a do? When you multiply all the output value, well, there. Let's do this, I'll multiply all y values on the graph by plus or minus. So that could just be a vertical stretch. If that a is negative, maybe it'll be a flip as well. The next things to deal with, and I believe both of these a second, because in fact it doesn't really matter what order you deal with these two in. What happens when you add a number to the input and then you add a number to the output value of a function?
It can go up or down, left or right.
Goes up or down, left or right. So this plus d is going to go right, nope, up by whatever that plus or minus d is. The plus or minus c is going to go left to the opposite direction as you expect by plus or minus c. And I guess the final thing is what happens when you take the input of a function, the x in the function, and you multiply it by some number. Well, what's it look like's happened? Let's just try to match up some similar points. So here's this point. That looks like negative 2/3. There's like a corresponding point on the purple graph. There's this turning point at x equals negative 1/3. Excuse me. Turning point, same y value, but the x value has changed. It looks like the x values have all gotten like squished together closer to the origin. That's what this will do. We'll take all x values, get divided by whatever that number plus or minus b is. So if that b is negative, maybe there will be a flip over the y-axis. All the x values will become negative. Feel pretty okay? This is what we did last time. Let's put this together. Let's just do one example, and we'll see. let's try to use this to sketch the graph. So start from y equals square root x. Get yourself to the graph of negative the square root of 2x plus 1 minus 2. So that'll be negative f of 2x plus 1 minus 2. And we'll see how people feel. Gesundheit. Either we do this all together, or I do some, well, either you do it and I be quiet, or I continue talking. People want me to continue talking through one more example of this? Yeah, cool, let's do it. So, according to this instruction for which move to do first, what part of this formula should we deal with first? So we're going to start with the square root function, square root of x, whose graph you just know. It's one of these elementary functions. There's the graph of square root. And it looks like I need to get that minus 2 there, that plus 1 there, this 2 in place, and this minus sign. According to the order that is said in the line above, what's the first of those I should deal with?
The minus.
Yeah, that negative sign in front of the square root. Because I want to take the square root function, that's a function, and negate that. And the instructions say do that first. So, the first of these intermediate steps that I'll graph will be negative the square root of x. And what does sticking a negative sign in front of a function do to the graph? Yeah, I guess like, I don't know how to write the instruction that it does that, but that's what it does, right? It's going to flip over the x-axis. Or multiply all the y values by negative 1. Whatever you want to describe this as, there's going to be a flip over the x-axis. So doing that, I guess that gets you there. There's negative the square root function. That feel pretty okay? So now look back at the thing we're trying to reach eventually. What's the next ingredient in that formula that we should deal with?
Left 1 down 2.
Right here on left 1 down 2. People agree? Nice. I don't like see it in front of me and my memory is very bad, so I'll believe you. Left 1 down 2. That'll get me at negative the square root of x plus 1 minus 2, and you just told me that I want to go left 1 down 2. You know what? Let's try to be consistent with the colors. Negative, because I still just have that negative, x plus 1 minus 2. So this point at the origin is going to go left 1, down 2, and then I'll see a copy of the same graph again. So far feel pretty okay? What's the only thing I have to deal with now? Cool. I see a 2 next to the x there. So the final thing I need to graph is negative 2 square root 2x plus 1 minus 2. Let's see, so first we dealt with the negative sign, then we dealt with the plus 1 and the minus 2, and now there's a 2 in front of the x. What's that going to do to the graph? Let's see, you're multiplying the x in the formula by 2, so like the intuitive thing,
Vertical stretch of 2.
Horizontal compression.
Isn't that the same thing?
Ooh, let's see. So, let's see, so a vertical stretch would be like all the y values get doubled.
Yeah.
So there would be a vertical stretch And a horizontal compression does something a little different. Instead of the y values getting more extreme, the x values will get squished together. And I think for this particular function, it will make a difference. Sometimes functions are symmetric enough that it doesn't. So, let's see, this 2, so this is going to be a horizontal compression. So the x values get divided by 2. So this point used to be at -1, 2. So where will that point be after this compression? Yeah, and the y value? Cool, yeah. Y value stays the same, x values get divided by 2. So you do that compression, there will be this point, let's even label it -1/2, comma 2. And from there the graph will look qualitatively the same. Still looks square rooted. Cool. Does that feel okay? So whenever you see a complicated function that's made out of a function that you know, and then just a bunch of linear things, just deal with each of those linear ingredients one at a time. And the end result will be the graph of this transform function. And you know what? Let's just like do one sanity check. Let's like plug in an input and see if it agrees with what our graph says. So just give me an input that you might want to plug into this graph. 0. X equals 0. Why not? Let's just do this quick test. This is just going to see if we've screwed anything up. Let's plug in x equals 0, see what we get. We get negative square root 2 times 0 plus 1, close square root minus 2. Gosh, I think that's -3. So 0, -3 better be on the graph. Does that look like 0 and -3 might be on that graph? See anything I've screwed up right now? I see one thing that I screwed up. That point has -y coordinate. Hopefully I have accepted it too. Really? Feel pretty good? Nice. So, we have now, that's the main point of today. We're just going to do some more things with it. Let's jump down here. And let's just see some more tricks you can do with this thing. So there's some function y equals f of x. It happens to be x cubed minus x plus 1. So let's use this to compare and contrast negative f of x with f of negative x. And we'll just see what conclusion, if anything, we can make from what we see. So negative f of x first, because I think that's the first one in the list. Yeah. What's that do to the graph?
Slope negative.
It makes the slope negative. Unless the slope was already negative, then it becomes positive. So I guess the most explicit way to say it is it takes everything having to do with a y value and makes it negative. I'm going to stick a negative sign in front of all the output values. So to go from here to there, I'm going to multiply all y values, get multiplied by -1. So that point right there where there's a y value of 0, that won't move. -0 is still 0. So that point will still be in the same location. It looks like 0, 1 is on the graph. Where will that go when I multiply all the y values by -1? X value stays the same, so X value is still 0, Y value of negative 1. All right, and I think those are the only two label points that I think I want to draw. So what do we see here? We see a nice little like upton. This will be the exact same, but flipped over the y-axis. This bit here looks like as the x values get negative, the y values get negative really quickly. So the x values will still get negative, y values will now get positive really quickly. Here's this bit where you see this little downton. It would be the same, just flipped over the y-axis. See a graph looking something like that. That feel pretty okay? All right. So let's also compare that with the graph of f of negative x. So to go from this function to the graph of f of negative x, what do you do to the graph?
Makes all the x values negative.
Yeah, all the x values will get multiplied by negative 1. That will flip it over the y-axis. What we do, we will multiply all x values by negative 1. So let's play the same sort of game. So let's start at the x-intercept. That's at like, I don't know, -1 1/4, 0. So where will that go when I multiply all the x values by -1?
It'll be flipped over the one.
Flipped over the y-axis, so same y value, x coordinate was negative, now it's positive. And it's a little bit more extreme than -1, so here it's a little bit more extreme than +1. I see a y-intercept there at 0, 1. So, doesn't change. X, the value of 0 times -1, still 0. Cool. Is that enough? Now you can interpolate it in between by following the graph? Yeah, I think so. In between the two intercepts, I saw this little upturn. Cool. Feel pretty good? All right, so now that we see without the aid of a machine in any way, the graph of these two transform functions, let's just see what conclusions do you think you can make? The two graphs we got, are they the same graph? No, so one conclusion we could make is, oh, this means f of negative x is not equal to negative f of x. So this function is not odd. But they look kind of similar to each other. Those two graphs that we have, that purple graph and that, no, red graph and that baby blue graph, they look similar, right? If you wanted to turn baby blue back into a red, just by looking at these two graphs, what does it look like you could do?
Translate it down, or in terms of the f of negative x.
Yeah, it looks like to go this way we could shift down. That seems about right. In fact, can you see how far you would want to shift down? 2, I think. At least I would get that y-intercept to line up with the y-intercept on the other one. That's the only coordinate we know on the nose anyway. Yeah.
Can you use it to actually help yourself figure out the problem, or is we just making a comparison?
In this case, yeah, this is just making a comparison. Because this is going to tell us something else. That means we could go from here to there by shifting down by 2. Oh, so that sure looks like that means negative f of x is almost the same as f of negative x, but shifted down by 2. What is shifting down by 2? What is that in terms of the formula? minus 2 on the outside. Cool. So by looking at the graph, we saw asymmetry on the graph. We saw that if you did these two transformations in two different ways, you got things that looked pretty similar. Just told you this result. And in fact, now that we see this result, do you think you can now like check that using the formula easily enough? Yeah. So, by looking at these graphs and transformations, you can see things that are easy to verify from the formula. But if I just gave you this formula and asked you, oh, how do f of x and negative f of x compare? Is there any meaningful comparison? There's nothing obvious to do. But if you look at the graphs, you can just see it. Nice. All right. So this next one, I think I really want y'all to do. So there's a function to graph, negative absolute value, 2x minus 3, then add 1. So sketch for me the graph of that function. If you've got a machine, you're totally welcome to use that machine to check your graph at the end. But go through the walk of getting this graph by hand. And if you want that extra bit of motivation, I'm going to ask like a problem on that exam item on Friday. That's going to be basically this. As you either make progress or come down to an answer, this isn't a test, so you can absolutely like compare with those around you. And compare ideas too. How do people feel about their end result? People feel about ready to talk? People want more time? Cool. Then let's maybe even jump right to what the end answer looks like. So this is built by starting with an absolute value function. So the end result should look something like an absolute value function. Upward opening absolute value or downward opening? Downward opening? What are the xy coordinates of the turning point? And if you didn't find them on the nose, then I bet you can find them right now, real quick. So I think the graph looks something like that. I want you to tell me where that point is.
1.5, comma 1.
I hear a 1.5 comma 1. Do I hear a second? Do I hear a disagreement? Cool. I think I see some faces indicating that there's some controversy. X-intercepts, both positive. Did you find them? How about just y-intercept? Where does the y-intercept wind up? And you know what, it is slightly unfair, right? In none of the previous examples did we do any individual computations for you to tell me points.
-2.
So the end graph looks something like that. Shall we go through it? Is there objections? Did I screw anything up?
You have -1.5. But you're drawing over risk 1.5.
Aha, aha. That's why people are looking at me like I was a lunatic. More like that? All right, should we go through the individual steps to get there? You know what, let's do it. So you start with absolute value function, you know what that looks like. And it's too hard to do all of the transformations at once. So which one of the transformations do you deal with first?
And then negative, that's in front.
Negative, that's in front?
Negative absolute value.
Cool. And what does that do to the graph?
Flips it over the x-axis.
Flips it over the x-axis. Nice. And I'm not worried about having a reasonable scale. There's negative absolute x. What next?
Yeah. You do -3 and then +1.
You do the -3 and the +1. Cool. What does that do to the graph?
It moves it right 3 and up 1.
Right 3, up 1. Cool. So let's just track this turning point. So right now that turning point is at the origin. I'm going to move that right 3 and up 1. And it's worthwhile to track interesting points like that. So right 3, up 1. And then before that, it looks like this thing has slope 1. After that point, the thing has slope -1. So that means I could even have tracked the intercepts at this stage. Neato, what's the last thing to do?
2 in front of the x.
Deal with the 2 in front of the x. What's that do to the graph?
Divide all x values by 2.
Divide all x values by 2. So this point used to be at 3, 1. Divide that 3 by 2 to get 1.5, and no one corrected me when I wrote a 3 there instead of a 1, but it was wrong, right? Cool. Folks feel pretty good about this? Nice. All right. One last thing before I want to crack into some stuff about quadratic functions. So you can graph anything that's built out of the things that you understand, any of the elementary functions, as long as you only do linear things to them. We've also talked about how if you have a piecewise function and you know the graph of each of the pieces, then you can graph the result. Let's put those together. Let's try to graph a piecewise function where each of the pieces is maybe just a little bit complicated. Yeah, let's do it. So let's consider the function f of x. 2x minus 1 if x is negative. 2x minus 2 quantity squared if x is between 0 and 2. And f of x equals 3 if 2 is less than x, or equal to x. So let's do that. Let's graph each of these things one piece at a time. So, and yeah, there were some like copy-paste errors that you'll have to correct. Let's start with the graph of 2x minus 1. Is that something whose graph you just know? Yeah, tell me about its graph.
Slope of 2, y-intercept of -1.
Straight line, slope is 2, y-intercept at -1. So, let's start here at 0, -1, and this thing has a slopiness of 2. I think that's a good enough picture for now. All right, and that seemed pretty okay. Next piece is 2x minus 2 quantity squared. Well, I think that's going to take like a few steps. Maybe you can do it all at once, but I'd rather not. So I'm going to give myself some space off to the side. Next piece is 2x minus 2 quantity squared. So see, that's going to be like, the elementary function to start with is the squaring function. So parabola, upward opening, and then let's figure out what to do to it. So if there's the just x squared function, and I want to get to that, what should I do first? I see like two things I need to deal with. I need to deal with that -2 and the times 2, right? I don't want to do them both at once, that'll get too complicated. What should I do first? Well, I'm going to flip back to the previous page that says the order to do things in. I don't know if you're being quiet because you don't know what I'm asking. So, when you want to do something, if you have a function that's built out of a function you understand and some linear stuff, first ask yourself, is that function multiplied by a number? Do that first. In this case, it's not. There's nothing there to deal with. Then, are there things added to the input or added to the output? In the function in question, are there either of those? Cool. I think it's just added to the input. So that means we need to shift in the horizontal direction by the amount that you add or subtract, but in the opposite direction that you expect. So this -2 is going to do something horizontal. We're going to shift right by 2. Nice. And the last thing to do, and I guess that point is now at 2, 0. Deal with that 2 multiplied by the x. What does putting a 2 next to the x do to the xy coordinates?
That's x values by 2.
x values by 2, it's something being done directly to the x, so it'll do something to the x coordinates. And it's the opposite of what you expect. All the x coordinates will get divided by 2. So that 2, 0 will become a point at 1, 0, and it'll open a board. So let's just copy that down. You have this turning point at 1, 0, 1, 0, and this thing opens a board. Cool. The graph y equals 3, what does it look like? Yeah, right, there's nothing to describe. It's the line at y equals 3. Cool. So, now let's just highlight the portions that we actually care about. I care about 2x minus 1 when x is less than 0. So there's the portion of that I care about. So let's label that down here. Right here at the point, it looks like negative 1, 1. I see a straight line coming out with negative slope right there. So far, so good. Where do I care about the 2x minus 2 squared part of the graph? For what x values? From 0 to 2. So from x equals 0, including, all the way on to x equals 2, which I guess is like there-ish. Excluding, I should copy down the parabola part of the graph. And we'll label some of these interesting points in a moment. So let's see, this point right here, this turning point was at 1, 0. Those two endpoints seem interesting. Let's figure out where those are. So how do you figure out where that closed circle is? Or just what is the address of that closed circle? I hear well, 0 fall, right? Unless you were doing the 2. I want to do the 0 one fall.
Sorry.
Yeah, I guess it's the same for each, same y coordinate. So how do you get this y value? Well, you plug 0 into that, you'll get 4. 0, 4. Same thing here. This is at x equals 2, so this is at 2, comma, 2 times 2 is 4, minus 2 is 2, squared is 4. All right, very nice. And then you copy down the graph of y equals 3 as soon as x is bigger than 2. So there's the graph of this piecewise function. Seem pretty okay? Nice. And Desmos is totally capable of graphing piecewise functions. The notation to get it to do it is a little bit ugly. But if you like that QR code, or if you just type into Google Desmos piecewise function, you'll find some randoms. Use that to help you check some answers. Cool. Feel pretty good about graphing? So let me close by pointing out that there is now an extra credit I want to advertise. There have been a few. There was lots of people who acted on the first extra credit, but no one's done any other ones since. I feel like I'm happy with that doing that. But we'll see what people want. There are some functions we haven't talked about. There's the function that rounds up, the function that rounds down, and the function that rounds normally. Extra credit. Graph those things. Figure out what sort of even and odd properties you get out of it. But maybe before we start in on the quadratic functions part of the notes, we got 6 minutes. We can either start the new packet, or do people want to do another piecewise graphing example? Cool, I'm happy to do that. Let's walk out this last one. So here is a piecewise function. It is minus x plus 1 squared plus 1 when x is less than negative 1. It is the absolute value function for x values between negative 1 and 1. It is minus x squared minus 1. Nope. It's the thing with. Each of those pieces, are those pieces you can graph? So you know what, let's start with this. I'm going to make you all do most of the walk, and then you'll tell me what to do. So step 1, graph those 3 pieces. Anyone feels unsure of how to proceed or wants some guidance in this last step, feel free to raise your hand and I'll come around. Come on, let's see how. Yeah, so in the previous example, there were all these gaps because the y values at the end was 1. So you don't see like the dot or anything there because they're just columns. An open's already good. All right, I see quite a few graphs that I'm pretty happy with. So you know what? Maybe I'll even start with this. One can graph this sort of thing using Desmos with maybe one issue you have to be aware of. So here's what I've done. I've pulled up a Desmos graph of this piecewise function. So really I've just graphed each piece one at a time and told Desmos where I care about that piece. People end up with a graph that looks something like that? Groovy. How many people drew a graph that looked something like that, but where like these points didn't line up or something? Okay, cool, yeah, because they should line up. They wind up being equal on the nose. In the previous example, there were these like jumps because the different pieces wound up at different endpoints. But that doesn't need to happen. Sometimes it doesn't. Sometimes this is a nice continuous function. And, in fact, so how did I get to this page to do this with Desmos? I started by Googling Desmos piecewise function and copied their demo. Because that's the way you use technology all the time, right? You never remember how to do something. A thing to be aware of. Notice all of those inequalities were strict in the pieces. And this graph just looks right, even though what I graphed is technically wrong. Desmos won't give you the open circle of Solidot at the endpoints. At least not in any way that I know. So yeah, even if you use Desmos to do lots of work, be careful with endpoints. Do those manually. Neato. Well, I guess it was really good that I handed out that extra chapter of notes because now you get to carry that around for an extra day. Take a look at that. It'll make lecture tomorrow seem very light if you already know what I'm going to say. I think that counts as both increasing and decreasing. Yeah, it has to go up some and go down some. Yeah.
Thank you.
Yeah. I mean,
It's a function of your personality.
and then yeah, I think that's, yeah, your graph will look better that way because it'll be computer generated. Depending on how much you like technology, it's drawing back, that seems like all. But yeah, if you want to use this to get an example, that's cool.
Thank you. Yeah.
I have a question of how it works. I think I'm going to leave the notes on the class, but I can tomorrow to help them.
Yeah, absolutely. Do I have a class? I have a class to ask.
Thursday?
Yeah.
Your office hours are between 8 and 11.
10 and 11. Yeah. In fact, if you want to shoot an email with some questions, some particular things you'd like me to, if you think there's anything that's answerable by email, go ahead and send an email too.
Thank you.
Yeah. See you tomorrow.
I had a question on what was the problem. It was, I think, making a rectangle out of parallel and perpendicular lines and then finding the area of it.
Yeah. Okay. So you're working your ways ahead in the web work. Okay.
Decent. It was marked as do it again this week.
This week.
There were quite a few do
Well,
it
yeah, I like.
Send me an email. That's definitely one. Yeah. We haven't covered that material. Yeah. Okay. Okay. So. Okay.
But I was just wondering about finding the intersection of two lines. Because from what I remember, it's set up with each other as all connect.
Oh, okay, no, that problem. Okay, yeah, okay, that problem is reasonable. Yeah. So if you have two lines that you found. So what is this point you are looking for? You're looking for a point where the y values are the same and the x values are the same. So both of these have that as their y value. So these two formulas have to be the same. And I'm looking for this point. Also open-ended.
Yeah, I tried that one, and what it gave me was a number that I think was right, but plugging it into either of them to find the y value gave me a point that wasn't that. When I graphed it on Desmos, it was the same actually, but it gave me either.
Oh, cool. It gave you different y values? Yeah, I mean, so let's go through this with this example. So if you come do this, add 2x, that's 5x, negative 6. If you plug in this x value and this equation, and you actually solve the problem, you'll get the same y value. Because you found this x value by setting these two things. Yeah, so go ahead and can you make my next time today?
Wait, do you know what time it is?
1 o'clock, I think.
Yeah, that's what I thought. It was like 1:15.
Yeah.
I don't think so, unless I come at 1:50.
Okay, so here's what I'd like you to do. You can come by at 1:50. I don't have like a 2 o'clock thing, so I'm still gonna be at the office. You can also send me like this question by email. And if there's just like other times in the day that like you can send me along some of those, and I can say, well, we can also meet at such and such time. Yeah.
I was just gonna say,
Don't need to wait before office hour. I'll be there.
I didn't realize this last minute, but is this point supposed to be 0, -1 for here?
Is that point supposed to be 0, -1? So you came from that point?
Yeah.
Which came from that, when x is 0, that's -1. Yeah, that better be 0, -1.
Okay.
Did I?
Because I wasn't sure.
Okay.
I realized, yeah.
Yeah, I goofed.
Okay, thank you.
Yeah. Thank you. This button.